Here's everything you need to know for static electricity for level 2 physics. Let's start off with what is matter. Matter is composed of atoms, which have a property called charge. And so here's an atom, and hopefully you're familiar with this. The idea that we have protons in the center, which have a positive charge, and we have electrons around the outside, which have a negative charge. Charge can either be positive or negative. However, the protons are attached to the nucleus, to the neutrons on the side, and so they don't move. We're only ever looking at electrons moving. And so if something is positively charged, that means there's an absence of electrons. That means there's more protons than electrons. That's what makes it positively charged. If something is negatively charged, that means it has more electrons than it does have protons. The way we measure charge is in this thing called the Coulomb, which is a capital C. And the charge on an electron is negative 1.602 times 10 to the minus 19 coulombs, and the charge on a proton is the same, except it is the positive. So hopefully you're seeing this guy, Mike Wazowski. I like to think of Mike representing 1 coulomb. He's round, and he's obviously got a lot of electrons. So how many electrons is he? Well, if we know the charge on a single electron is 1.602 times 10 to the minus 19, if I go 1 divided by that number, that'll tell me what 1 coulomb is. And so 1 coulomb is 6.24 times 10 to the 18 electrons. Or in another way of saying that, he's 6 million electrons. And that idea is a really important idea, because when we get to current, we're going to say that 1 coulomb moving past a point every second is how we define 1 ampere, 1 amp. So what is current? Current is the rate of flow of charge, i.e. the amount of charge that passes a point in a given amount of time. And so we have this equation here. We have the number of charged particles, the individual charge, and then the total charge measured in coulombs. So example, we have 1 million electrons passing in a wire. How much charge is there? Well, there's 1 million, so that's the N, the baby N. And what's the charge on a single electron? Well, it's 1.602 times 10 to the minus 19, and this gives us the total amount of charge. That's not the current, but that's the total amount of coulombs of charge going past a point every second. So what is current? Well, current is the symbol I, measured in total charge divided by a period of time. And so if we were to look at this, we had 1 million electrons, so that amount of charge divided by 2 would give us 8 times 10 to the minus 14 amps. And so in class you would have done this experiment here where we had some rods and we rubbed them with different cloths and we put them close to each other. And so what we would have found is that like charges repel and unlike charges attract. So if we had a glass rod and it was rubbed with some silk, it became a positive charge, and if you had both glass rods both rubbed with silk and brought them next to each other, they would have repelled, they would have moved away from each other. Charge wasn't created through that rubbing process. An equal amount of negative charge was then placed onto the silk. In a similar way, if we had an ebonite rod and it became negative, and then we had a glass rod, then those opposites attract, and so the positive would have attracted to the negative. And so we would have seen that there was some sort of force happening, and which one became positive and which one became negative was related to this triboelectric series, and that's actually not part of the standard. And so we could have rubbed 2 balloons with the same cloth and got that same kind of idea, this idea of like charges repelling. And it's not a foreign idea, this idea of invisible fields. So we've used magnets before and seen magnetic fields. If you have a mass and you raise it above the ground, it'll fall towards the earth, and so we've seen a gravitational field. But the field we're looking at in this unit is an electric field. So an electric field is an invisible region in space where the electric forces can be detected. It's depicted using electric field lines, and the direction of the field is shown by an arrow. Without an arrow, you get not achieved. I like to say that positive people are giving people, and so the field lines come out of the positive charge. Negative charges, maybe like slightly negative people who are always about themselves or self-absorbed, all the field lines go into them. You can interact with this animation here. I think the link's just above, and you'll be able to see that like charges repel. You'll notice that the field lines never touch, and they come in and they touch at 90 degrees on the charge. We've seen that opposites attract and like charges repel, and that they can be separated using this process of friction or rubbing. Charges aren't created, they're just moved. we can have areas of strong field where there's lots of field lines and areas of weak field where they're not. And so you can interact with John Travoltage here if you'd like to. He rubs his foot on the ground, and the more he rubs, the more charge he gets, and then he goes zap, doesn't he, as he discharges. What you're most likely going to be assessed on in level 2 is this idea of a uniform field, which is shown by equally spaced lines. So these need to be equally spaced, and they need to go from one plate to the other. As we've said, positive people are giving, so they go from the positive into the absorbing negative plate. And we have these field lines that are non-uniform or non-uniform fields at the end, and they are also essential. How do we define electric field strength? Electric field strength is defined as the voltage between two plates divided by the distance between them. So, notice that there's a distance d here. We're going to come up with an equation soon for energy, and that's also got a d, but those two d's are not necessarily the same. How do we make this make sense? It's probably best done with an example. So, a charged particle, minus 4.8 times 10 to the minus 19 coulombs, is suspended within an electric field. How many electrons is this equivalent to? Well, we know the charge on a single electron is 1.6 times 10 to the minus 19. So we're asking how many lots of 1.6 fit in 4.8. So 4.8 divided by 1.6 will give you that answer. If we were to think about what's happening in terms of this electron inside of here, we'll see that the bottom plate is attached to the negative, and so that's why it's negatively charged. The top plate is attached to the bigger one, which is positive, and so that is positively charged. That was the 4.8 divided by 1.6. What is the electric field strength? That's going to the equation we just learnt, E equals V divided by D. There's 1,000 volts between these two plates, and there's a distance of 0.05 meters. And so we get 20,000 volts divided by meters. How can you increase electric field strength? Well, there's two ways. You can either bring those plates closer together, or you can increase the voltage. Which direction will the charged particle move due to the electric field? So this is a negative charge, and so the negative charge is going to be attracted to the positive plate because opposites attract, and so the electric force is going to be in the upwards direction. If we were to draw the electric field lines, they would go from positive to negative, equally spaced, touching both plates with some curvies on the side. Next, we're going to be looking at force on a charged object inside an electric field. A charged object inside an electric field will experience a force, and the way we can determine that is using this equation here. So force measured in newtons is equal to electric field strength times the charge that electric field strength is acting on. A negative charge will be attracted to experience a force towards the positive plate, and a positive charge will be attracted towards the negative plate. We've done Millikan's oil drop in class. Essentially, you spray some oil into this chamber, and there's an electric force in one direction, which in this case has to be up, and weight force, mass times gravity, in the downwards direction. When those two forces are balanced and it's stationary, it will just sit there floating for a long time, and so you can interact with this animation here, and it looked a little bit like that in class. So let's see if we can do an example that will bring that to life. So if a charged particle has a mass of 2.73 times 10 to the minus 30 kgs, and is that charge, what voltage would be required to keep the electron suspended in the electric field? The first thing we need to know is what is its weight force. And so we'll go mass times gravity. We've got the mass, we'll times it by 9.8 or 9.81, and that'll tell you there's a weight force. So there's a 2.7 times 10 to the minus 29 Newton force going downwards, and so if it's going to be suspended there, there has to be a force equal in magnitude but opposite in direction. And so now we're going to use F equals EQ, and so we're going to try and find out what is the E. So if I go F divided by Q, that'll tell me the electric field strength. So I know the force must be the same, and I know the charge already. And so, but divide those numbers, I get 5.57 times 10 to the minus 11. That's the electric field strength. I now need to use the first equation that I learnt, that E equals V over D. I'm trying to find what the voltage is. So voltage equals electric field strength times distance. I now know what the E is, I know what the distance is, and so I can work out the answer. I need a 2.79 times 10 to the minus 12 volt voltage across here to keep those two plates, to keep that electron suspended between those two plates. Electric potential energy. this is kind of the last big idea of static electricity. So an object above the surface of the Earth has gravitational potential energy. So we're very familiar with a gravitational field. If I have an object and I drop it, it'll come down and hit the ground. And the reason behind that is there is a weight force, that an object has mass and the acceleration on Earth is 9.8 meters per second, and so that is the force of gravity. In a very similar way, we have electric potential energy. So a charged object inside a uniform electric field has electric potential energy. So in this case, this negative charge is attracted to the positive plate, and so it would like to travel here. So at the moment it has electric potential energy, and as it begins to move towards the positive plate, that electric potential energy will be converted into kinetic energy. The force acting on that is F equals EQ, as we've just seen. The higher you hold something in gravity above the Earth, the more gravitational potential energy it has. Also, the more work is done to get it there. A similar kind of idea in electric fields. So work is done. Another name for work is change in energy, which is force times distance. So the more force I apply, or the larger the distance it is, the more work is done, the more gravitational potential energy it has. You notice this time this distance is between the charge and the plate. It's not between the two plates. And so we saw earlier E equals V over D. That's a different D to this one. And so what is the work done? Well, work is force times distance. We know that force is already EQ, and so the work done is going to be EQ times D. That's the amount of work done to move that negative away from the positive. It's also going to be equal to the work done from that negative moving towards the positive. If a mass is raised further from the ground, it gains more gravitational potential energy. If a negative charge moves closer towards the negative plate, it also gains more electric potential energy. Let's go for a bit of an example and see if we can make all of that make sense. So find the electric field between the two parallel plates. And so we have a voltage of 400 volts and a distance of 0.05. That'll give us 8,000 volts per meter. If the electron moves 0.3 meters, how much work has been done? And so we know that work is force times distance, and we know that force is EQ, and so really we're looking for work equals EQD. We know the electric field strength, we know the charge, and we know the distance, and so that tells us the amount of energy. And that really big hint, those D's are not the same. So assuming there's no gravitational effects, how fast will the electron be moving? This is often the merit or excellence question, and so we're going to be using the year 11 idea of conservation of energy, that potential energy equals the kinetic energy, and so we're going to say that this number here, 3.84, is going to equal to a half mv squared, and we do some algebra. You can simply type that into the graphics calculator if you're not very confident in your calculations, and you'll get a speed of 9 times 10 to the 6 meters per second. And so those charged particles can actually move quite fast. Continuing to explore that idea of force on a moving charge, sometimes you can shoot an electron across an electric field, and so in this case the electron is moving from left to right, and as it enters it's negatively charged, and so it's attracted to the positive plate, and so it'll go up because opposites attract. The same idea here, the negative charge is attracted to the positive plate, and so it'll experience a force downwards. This force won't change its horizontal speed, it'll only change its vertical speed, and the same idea with a positive charge there. There's a bunch of other worked examples in the booklet. If you'd like to see some more on those, then click this video here and I'll go through the answers to the questions in the booklet. Otherwise, that's electrostatics. I hope that makes a whole bunch of sense.